Okay, hello everyone. I'm sorry for the delay. Okay. So, nice to meet you again. I hope my last lecture is helpful to all you guys. If you have any questions, feel free to ask me anytime during the lecture. So let's begin today's lecture. Today's topic is on the Mergesort and Quicksort. Before we go into today's topic, let's take a look at the problem of the day first. So the problem of the day, given an efficient algorithm to determine whether two sets of M and N are disjoint. Analyze the complexity of your algorithm in terms of M and N. Be sure to consider the case where M is substantially smaller than N. So let's say we have a set A, and we also have a set B. Let's say if the size of A is M, and the size of B is N. So can you give me any algorithm to determine where the two sets are disjoint or not? Note that the M is substantially smaller than N. Yes?
I would say that first we should sort the sets. So using a Quicksort on both of the sets, we're able to have all the numbers in order.
So you want to sort all the sets or only one set?
I want to sort both of them.
So what you are saying is that you want to sort both A and B. And then what you are going to do?
We have to walk through them and
Compare the numbers?
Yeah.
So that you want to merge them to one sorted list. Is that what you are talking about?
Yeah.
Great. And then how do you decide if the two sets are disjoint or not?
Well, I guess like when we realize that one of the numbers is in both of them, then at that point maybe we can print something and then return it.
Okay, great. So let's redo it. So first of all, you want to sort A, and how long does it take?
And log n.
A with the size of M.
How long does what take?
So A, the size of A is M. So how long does it take for sorting A? Okay, so for sorting, usually if the size is M, the sorting will be M log M.
M log n.
Yes. So let's say we are giving a M log M for sorting A first. And then, as you said, we are also doing a sort on B. So it will be N log N. And now, after the sorting, let's say we have two arrays that it is sorted in the sorted order. So what you are saying that begin from each array, you are comparing each element and maybe add them or just to merge them into the same list. And whenever we find two elements that is the same, it means that the two sets are not disjoint. By the way, does anyone have a problem with the definition of disjoint? Okay, great. So yes, can you tell what's the total time cost for this one?
It would be like M log n plus N log n.
Yes. And when you compare it, how long does it take?
All of n.
Yes, great. So we have the first algorithm. So let's say we have the first algorithm is to sort both A and B. And then the time will be M log M plus N log N plus N. And what's the final result for that? Can you tell what's the answer?
I think we would
Yes.
Between either the m log m or the n log n?
Yeah, because that m is substantially smaller than n, so the,
Take the n log n.
yeah, very good. Yeah, this is n log n. It's a very good try. But let's think about one thing. So n is substantially larger than m. So imagine that, for example, n is greater than 2 to the m. So what will happen? If we have an n which is greater than 2 to the m, then it means that this complexity can be greater than n times m. Okay. So it means that it can be greater than n times m. Can you think about another algorithm that has a better efficiency? Yes, please.
Or could just not sort where you just take whatever set is smallest
Uh-huh.
and then go to those elements and check if they're in the other set. You don't need to use sorting.
Okay, great. So you are saying that we can just sort the smaller set and then check it by going through the other larger set. In this case, the smaller set is A. So sorting A, it will be m log m. And by going through the B, it will be O of n. So what will we do? First, we will sort A, and we get a sorted array. And then we can go through the B. We have a loop. Like we loop through the element in B, loop through B. And for each element in,
Sorry, I didn't mean to say sort A. You don't have to sort either. You just go through the elements in A. No sorting.
so if you don't sort it, what will you do?
And you can just iterate through the sets, right?
Yes, you can iterate through A. So if you iterate through A and B.
If those elements are in B.
Oh, sure. I would say that is a brute force search. So you are having any element in A and any element in B, and you are comparing them one by one. So what will be the complexity for that?
All of M.
Huh?
All of M.
Oh, why is it O of M?
Because you're only checking the elements in A.
But if you only check the elements in A, how do you compare it with the elements in B? Yeah, so you want to know if there's an element in A that also exists in B. If the element exists, then the two sets are not disjoint. Yes, so now what you have is that you are going through set A. So there will be m elements. So suppose now you are at some element A, you got the element. What are you going to do to check if it's in B or not?
Use like the Java contains method.
Contains. So if you are talking about Java's contains method, I'm guessing that you are using the hash map.
Yeah, or hash set.
Yeah, okay. So this is also a good idea. It's about the hash set and the hash map. For the hash set, so let's say now we are going through A. There will be m elements. And now we want to check if the element is in B or not, and we construct a hash map. So the expected time to find if the element is in B is 01. But note one thing. I'm mentioning the expected time. So can you tell what will be the worst case, in the worst case scenario? How long does it take to find the element? If in the hash table, how long does it take in the worst case scenario? O of n, yes. So in this case, the total time we need in the worst case scenario will be m times n. So let's say here, let's say maybe hash map, hashing. So actually it will take O of mn. But again, so this is the worst case scenario, and in practice, what we will usually have is O of 1. So it's a solution that is good in practice, but not in the worst case scenario. but still it's a very good try. Now, can you think about another algorithm that have the better complexity? Yes, please. By sorting M, you mean the set A? Yes.
And then you iterate through every element in the bigger one.
Mm-hmm.
Binary search to find if it exists. So it would be yeah, I think check if it exists. So it would be like analog and.
Yeah, sure. Let's try. So what we are talking about is that first we will sort the smaller set. Here the smaller set is A. It has M elements. For the sorting, it takes M log M. And now we are going through the larger set. So it has N elements. And what we do is to perform a binary search on the ones we had for A, and then check if it exists. So let's check the complexity. Now, sorting is M log M. And we also have the B, which is we loop through the B. And since there are N elements, let's say it takes N. And for checking, if one element exists in A, it will be log of M. So the total time will be N log M. And let's add them together. So sort A only. In this solution, we will have the M log M plus N log M. As we know that M is smaller than N, so the final answer will be N log M. And we need to compare the two solutions. So we have the both N here, and for the N is greater than M. So we can see that the third solution is even better. Now, can you think about other algorithm? Let's try a different way. Oh, yes.
Using the union find algorithm,
Mm-hmm.
with disjoint sets, check if particular values in both of the sets,
Mm-hmm.
and that would give us what went worst case.
Yes. Yeah, but today I'm going to add another solution, which is for the comparison of the here. So now we are only sorting the A here. Can anyone answer the question that if instead I sort A, what will happen if I sort B and find the element in A? Oh, sorry, iterate through A to check if it's in B. What will be the complexity? Can anyone do that? It's very similar to the third solution. Yes? M log N. Great. So we have another one, which is very similar here. So let's say it's a fourth solution. It will be sort B. And you are saying that it will be M log N. Okay, let's check. So first of all, we are having the N log N to sort the set B. So that's the sorting step. And then we want to check if the element is in B or not. So it will be M log N. And now, which is the dominant term? Yeah, it will be N log N. And if we compare the two solutions, we can see that we both have the N terms, so we can ignore it. And now for the log M and the log N, the third solution is still better. So can anyone see the difference between them? So first of all, when we sort both sets, it doesn't seem like it gives us the best solution, the most optimal way. But instead, if we only sort one set and iterate through the other set, we can see that we actually get some efficiency here. And also, which set you decide to sort will give you a different performance, so you need to be very careful about it. Do you have any questions? If you have any part that you don't understand, just feel free to ask. Okay, great. So this is a problem of day. And now let's go to the merge sort. So first of all, merge sort is a recursive algorithm. So a nice recursive approach to sorting involves partitioning the elements into the two groups. And for the merge sort, it will partition the array into the left part and the right part. So I think, do you have any question about the recursive? For the recursion, it will be, I have a problem, and I want to divide it into two sub-problems. And it is the same as the original problem, like I have a watermelon, I cut it into two, but the two parts are still watermelons. If I cut the smaller watermelons, it will be an even smaller watermelon, but it is still the watermelon. So that's a recursive. Okay. So let's see, how does merge sort do the partition? So for the merge sort, first of all, you will have an array. And here in the code here, it will be the item type S. And then you will have the two pointers. So the left and the low and the high. You can just think of them as the left end and the right end. What you need to figure out the first is the middle point. So after you find the middle element, what you need to do is that you want to do the merge sort on the first on the left half and also on the right half. So here, as you can see, that you will have the two merge sort calls. And the first one is from the low to middle, which is the left part. And then it's the middle plus 1 to the high, which is the right part. Do you have any question? So that's the recursive part. And then after you have the recursion, you will perform an operation called merge. So you will merge the two half paths and into one array. So do you have a question for now, like about anything? Okay. So where does the efficiency of the merge sort comes from? It comes from how efficiently we combine the two sorted halves into a single sorted list. So the smallest element can be removed, and you leave the two sorted lists behind, the one slightly shorter than before. And you can repeating this operation until both lists are empty and merges the two sorted lists into one array using an n-1 comparisons or log O of n of the total work. Let's say we have two arrays here. So now we have the array A, which is 5, 7, 12, 19. And another array, which is B, of 4, 6, 13, and 15. So how do we merge them? Remember one thing, that the list is sorted. So we know that, let's say now we are having them in the increasing order. What we can do is to simply have some pointers, like maybe not the pointers, let's say it's a stack or the queue. So you can think about that we begins from the first element. It should be the smallest element in the list. And then we compare them. Which one is the smaller one? Now, here if we compare 5 and 4, you can see that 4 is the smallest one. So we add it to our result array. And then we remove the 4. We are at 6. Now we are comparing the 5 and 6. And then we see that 5 is the smallest element. So we have the 5 here. And now for A, it will be 7 is the smallest element. So in this case, let me just do it quickly. So it will be 6 and 7, it will be 6. And we remove it. Now we have 7 and 13, it will be 7. So we remove that one. Now 12 and 13 is 12. So we remove it and goes to 19. And now 13, 19 is 13. And 15. And now it's 19. And then we see that both A and B will be empty now. So we finish the merging part. How long does it take? It will take only O of n because we have only n elements. So the comparisons we did is actually n minus 1 because we don't need to compare for the last element. Okay, do you have any questions? So this is this is the efficiency of the merge sort comes from. Okay. And this is the code for the merge. We have the 3 pointers. We have the low, middle, and high. And now we have 2 buffers. So do you know the data structure of queue? Okay, great. Yeah, so for the queue, it has a property of first in, first out. So what we do here for the first 2 loops is that we first include the left part in the sorted order. And then we include the right part to another queue, which is also in the increasing order. And now we are in a while loop. The while loop is to check whether any of the queue will be empty. So if none of the queue is empty, what does it mean? It means that we need to perform the comparison on the smallest element. So now, suppose both of the queue is not empty. Then we will check what's the head queue function. You can imagine as the dq function so that it will give you the smallest element, which is the head. And then you will compile them and dq the smallest one. So as we did here. So when you are at the beginning, the first buffer will return the 5. And the B, for the second buffer, it will return the 4. And you are checking if 4 is smaller than or equal to, 5 is smaller than or equal to 4. And you see that 4 is smaller, so you dequeue the second buffer. And then add it to the S here. So this is a 4 where you add it. And here you can see that actually our array is kind of balanced, equal size. So when we are only have the 19, it has only 1 element remain. Let's think about another case. Let's say we have 1, 2, 3, 4, 5, 6, 7, 8. So what will happen? You will see that the 1 will go here, 2 will come to here, 3, 4. We did only 4 comparisons, and then A is empty. But B is like it has all the elements as original. So at that time, we don't need to perform any more comparisons. We can simply add the element to the result array. Okay? Do you have any questions about the code? Okay, great. So I think you have a good understanding about the merging. So you don't have any question about the partition? So so when we perform the partition, what will be the condition of the last layer? So what we want is that when we have the problem, what we want is an array, and we want the subarray to be sorted so that we can perform the merging step in ON. But how do we guarantee that our two subarray is sorted? Okay, let's imagine it like a tree. So for now, we have a unsorted array here, and we partition them into two parts. And we want to keep partitioning them. So the size of the subarray will be smaller and smaller. But when will be the time that the subarray is obviously sorted? Yes? Yes? Yes, great. So if you go down to the bottom, like when you have only an array with size 1, it will be obviously sorted. So that's what you know, that at the very bottom level, I have two sorted subarray, and I can merge them into a larger sorted array. Do you have any problem with this step? So at the bottom, I have the two sub-problem that it gave me the two sub-sorted array, and I can perform ON into a larger sorted array, like one here, and I have one here. So it means that when I return, it will be an array of two elements, and it is sorted. Okay?
Sorry, this is unrelated to the problem, but could you maybe draw on the board instead, like on the smart board? Easier to see the arguments.
I can try to use my cursor. Huh? Yeah, it's my laptop. Thank you.
Does it work? Don't ask me why.
But what should I do for now? Thank you. So I should.
How does this work? Display. You need to check for external display. Multiple displays. Where to go? There we go. Oh wait. Okay. Oh, wait.
You can go down.
Oh yeah. Go down, but I can't. Okay, there we go. 1, 2. There.
Okay, great. And
This
I can just.
Oh, keep changes before. All right. Where is? All right, try now.
This way?
Does this work? Wait. Should in theory work.
This is a PDF drawing.
Oh, there's a PDF.
Yes. Do you want to draw on the screen or something else?
Well, the open paint should work. I'm just bending it. Oh, that's why, because it's connected here.
Oh.
You have to draw it here, I think.
Can I draw here?
Yeah, you have to connect it to. You have to connect your laptop to here in order for this to work.
Okay.
Yeah. Can you connect the?
I think I'm using the HDMI.
Connect your laptop.
Yes.
So why is wait? If it's connected here, then why is that?
It shows the laptop.
Yeah. Oh, there we go.
Okay.
Wait, it's sort of.
Sort of, kind of. Yes, I think I can work on
Okay, I
that.
guess
But
you
how
work
can
on
I
it.
erase it? How can I erase it?
Oh, you have to kind of. There's. Find the erase button on here. There we go. That's erased, but then it's really annoying to get back every single time.
Anyway, I can draw the graph first. Maybe.
Yeah, you could try drawing first.
Thank you. So, okay. Okay, now we have an array, and let me see if I can find the right position for that. Okay. No. Can I reset it? Okay, one sec. Let me see if I can. I guess I can use some shapes like this. Can
Should we try using that HDMI? Because this is currently not connected to here.
maybe I can just change a pen.
Change what?
The pen.
Pen?
Yeah. Yeah. The marker.
Yep.
This one. Okay.
Well. Sorry.
It's okay. Thank you for your help. Thank you. It still was to have a try. So, okay, let's change the marker and there's it now. Okay, great. Maybe for this part is harder to feel, so I will write it here. So when you go all the way to the end, like here. So when the array is with only one element, it's always sorted because it's only one element. So what do we know is that when we have the two sub-array, in return, we can have the sorted array of 2 in O of 2 time. So in this case, we can know that for all the sub-problem, we can have the 2 sorted array returned. So that when we perform the merge step, it will take only O of n to get the sorted array. So does anyone have the problem on this part? Okay. So that's the partition and the merge. Let's see if I can go back. And this is a tree for the Mergesort analysis. As we can see that the top blue array is the original array, and we partition them into the two sub-problems, which is the same problem, but it's like with a smaller size. So it has a darker blue color. And then also on the third level, we will have the super dark blue level with the 4 sub-problems in total. So what will be the height of the tree? If we partition each problem into 2 sub-problems only, so the height of the tree will be, yes? Great. Yes, it is log n. I have a question for you. How many nodes are there in this tree? Yes, please. Huh? Yes, how do you get that? I guess you are using the function. So let's say we have 1 node here, and then we have 2 nodes here, and then later we will have the 4 nodes and all the way to the end. That how many nodes are there at the bottom? It will be n nodes. So it's 1 plus 2 plus 4 and all the way to n, and your answer is correct. It is 2n minus 1. So someone may be questioning about that. I can give you another way to figure it out. So let's say we have a function which is Sn. It equals to 1 plus 2 all the way to the n. And now if we do a multiplication on it, we have the 2 of Sn. So what will the equation be? It will be 2 plus 4 plus n plus 2n. So for this one, do you have any questions? Yes?
Is it 2n minus 1 or 2 to the n minus 1?
Sorry?
Is it 2 to n minus 1 or 2 to the power of n minus 1?
It's 2n minus 1. Yeah, I will explain why in a math way. So now we have the Sn and the 2 of Sn. What can we say that if we want to get the value of Sn, actually the Sn equals to 2Sn minus Sn. Did anyone see that? If you cannot view it, I can write it on the right. So we have the Sn equals to 1 plus 2 plus 4 and all the way to n. And also we have the double, twice of it, to be equal to 2 plus 4 and all the way to n plus 2n. So it's just the multiplication of it, and you do that. And now what we can know is that Sn equals to 2Sn minus Sn. So we will have the result that if you subtract the Sn from the second equation, then we can see that we can subtract all of these. And we have the 2n and the 1 in the first line. So it will be 2n minus 1. Do you have any question? Okay, great. I hope it can help you understand by using the formula. And now let's think about the worst case. So the worst case, what will be the time complexity of the worst case, and how did you get that? So for each level, we are performing some operations, and it is counted as our work. Let's say at the first level, when we are doing the merge, there are n nodes. So in worst case scenario, we need to compare all the elements until there is only one element remained in the one queue. So in that case, we need to perform n minus 1 comparisons. Hence, at the second level, we have two subproblems, and each problem has n divided by 2 elements. And the total work will be twice of the one subproblem work, which is n divided by 2 minus 1. And by calculating the sum, it will be n minus 2. And also we can see that for the third level, for the same reason, it will be n minus 4. So what will be the total work for all the levels if you sum them up together? Recall that the height of the tree is log n. Yes, please.
So it's simply n log n minus 2n minus 1, so that's beta log n, or n log n.
Yeah, so what will be the dominant factor?
The n log n.
Great. Yes. So the worst case time is n log n. So you can think about it like for each level, you will have the O of n total work, and we also have the log n levels, so you can multiply them together, which you get the n log n. Okay, great. So the idea we used in the merge sort is the divide and conquer. Divide and conquer is an important algorithm design technique. Using, for example, we have the merge sort we just mentioned about. We also have the binary search, the fast Fourier transform, and also the strengthened matrix multiplication algorithm. So in this kind of problem, we divide the problem into two smaller subproblems and solve them each recursively, and then meld the two partial solutions into one solution for the full problem. This is another way for you to think about the complexity. So let's say if the t will be the total time we need to use for the problem. So we have the tn. Here in the merge sort, we partition the array into two equal size. So each problem will have the size of n divided by 2. And we know that the time will be t of n divided by 2. And we have two subproblems. So for the partition part, we will have 2 times t of n divided by 2. But after the recursion, what we are going to do? We need to do the merge operation. And for merge, it takes linear time to perform it. So the time will be theta n. And using this formula, you can see that the t of n will be theta n log n. Some other thing to mention about that, does anyone know the differences between the RAM, the memory, and the disk? Okay, if you have any question, you can ask. Okay, so when we are talking about the sorting algorithm, usually we are talking about the internal sorting, which means that the sorting operation is performed in the memory, or you can say in the RAM. So it is very fast. But what if the thing that we want to sort is too large that it cannot be put in the memory? For example, we have the Google. The Google needs to sort all the websites and give us the rank 1, rank 2 as a search result. But there are so many websites in the world. You cannot put it in only the memory of one computer. So in that case, you need the external sorting. It means that you put the thing that you want to sort on the disk. So what will be the difference? The difference is that it is very slow to access the disk. So when you are thinking about the external sorting, the bottleneck is actually the read and write times. For here, does anyone have problem? Okay. So as you can see here, disks are much slower than the main memory, and it benefits from the algorithm that read and write data in the long streams. It's not the random access, which is the RAM. But for usually the merge sort will have a good performance on the external sorting. And later we will talk about the best algorithm on the internal sorting. Any questions? Okay. So the best algorithm in the fastest internal sorting algorithm is Quicksort. So for the Quicksort, it also has the partition, but it is different from what we have in the merge sort here. For merge sort, you simply divide the array into two equal sides. But for the Quicksort, you need to find a pivot. So let's see if we are using the example here. Is it easier for everyone to view? Okay. So here we have 8 numbers, which is 17, 12, 6, 19, 23, 8, 5, and 10. Let's say we simply choose the rightmost element as a pivot point, which is a 10 here. So what is a pivot point? The pivot point is the number that you use to sort the array partially. So after you have the pivot point in the array, so all the elements on the left of the pivot point will be the numbers that are smaller than it. And all the elements on the right of the pivot point will be the elements that is greater than the pivot point. For example, now we have the 10 here. Let's see that 17 is greater than 10. So 17 here. 12 is greater than 10. So 12 here. 6 is smaller than 10, so it should belong to the left part. We have the 6 here. And 19 is greater, so it's on the right. 23 is greater. It's also on the right. And 8 is smaller. 23 was greater, and 8 is smaller, it's on the left, and 5 is smaller, so it's on the left. Then we can see that the 10 is at the 4th position in the array, and all the elements smaller than it is put on the left side. All the elements greater than it is put on the right side. So for here, do we have any questions about the pivot point? How many comparisons did I do? N. Great. So actually it's n-1, but it's of the ON, which is correct. So for this one, the sorting is only ON at this level. And there is one thing to note, that we not only know that the elements here are smaller and the elements on the right are greater, we also know that the position of the pivot point will be the final position in the total order. You need to notice this one. So this is a key point. So in this case, actually we partition the array into 3 parts. The first one is the pivot point that we chose for the current sorting, and also the left part, which contains only the smaller elements, and the right part, which contains only the greater elements. But you need to notice that for the left part and the right part, it is still unsorted. It just have the regulation about whether it's greater than or smaller than the pivot point. As we scan from the left to right, we move the left bound to the right when the element is less than the pivot. Otherwise, we swap it with the rightmost unexplored element and move the right bound one step closer to the left. That's the partitioning. So why do we need the partition? As I mentioned. So first of all, the pivot element ends up in the position it returns in the final sorted order. And also, after partitioning, no element flops to the other side of the pivot in the final sorted order. Do you have any questions on the second point? Okay. So to notice that for the second point, when they have no interactions with each other, it means that the two parts actually is independently. So it gives us a recursive sorting algorithm. Let's take a look at the pseudocode. So now we have the function of the quicksort, and we are still giving a s, which is an array. And we also give a point of the low, index of the low and the high, which is the left and right. And now the p here, actually what the p is the returned value from the function of partition. So what does function partition returns? It returns the pointer, the index of the pivot point. So let's say we have the example of the 10. And actually, after our function, the partition function will return 4, as the pivot 10 is at the index 4. So in this function, the p will be 4. And now we have two recursive call again. The first one is from the L, which is like at the first level, it will be from 0. And now we have the p equals to 4, so it will be 4 minus 1, which is 3. So we will have the first recursive call on 685, the left part of the array. So the left part, the array which is on the left of the pivot point. And then we will perform the quicksort on the right part. So it will begin from index 4, which is 23, and all the way to the right, which is 17. So we will perform a quicksort on 23, 19, 12, and 17. And so on, when we will have the lower level recursion. Do you have any question for this part? Okay. And let's take a look at the code for the partition. So here, you will have the index I and the pivot element index, and also the first high. So this algorithm, actually, they simply choose the last element as the pivot point, as we had here. So the high, let's say at the first level, the L will be 0, and the high will be 7, as there are 8 elements. So L will be 0, and H will be 7. So let us pivot point be 7. And then we compare the elements from the beginning. So we'll compare the 17 to 10, 12 to 10, 6 to 10. And whenever we find a element, or we need to perform that is smaller than it, we need to perform the swap. And then we also increase our counter of the first high to +1. So in that case, after we finish the for loop, we will know that there are 3 elements that is smaller than the pivot point. And so our final pivot point index will be 3 here. Do you have any question on this? this is how you find the pivot point index, and also it also sort the array by the pivot point. One thing to note that this is actually an in-place algorithm, so you don't need extra memory, extra space for that. You can simply do a swap. Okay? Okay. So let's think about what will be the best case for the quicksort. So when we divide the quicksort, we see that there are a difference between the quicksort and the mergesort. By mergesort, we simply divided them into the two equal sides, so that the height of the tree will be log n. However, in the quicksort, when we choose the pivot point, it can have different numbers of elements on both sides. We can have the equal size as mergesort. Like if we have another element 1 here, then we will have 4 elements on the left and 4 elements on the right. But what if we choose 8 as our pivot point? What will happen? If we use 8 as our pivot point, we will only have 1 element on the left side and 6 elements on the right side. So what will be so the height of the tree will change. And in that case, it may not have the best performance. But now let's just assume that we will have the best performance. So first of all, to get the best performance, we need to have the equal size. Assuming that we are lucky, we choose the best pivot point in every level. What will be the time complexity? Yes? Yes, it is n log n. So assuming that we are super lucky that we have the best pivot point, which is just the middle element, so we'll have equal size on for both subarray. And in this case, we will get the similar complexity as mergesort, which is n log n. Let's take a look at this tree. I think it's easier to understand. So in quicksort, we will divide the array into 3 parts. The first one is the pivot point. It's only an element, so it's the length of 1. And then the left array and the right array. So the total partitioning on each level is O(n), but it takes log n levels of the perfect partitions to get to the single element subproblem. So when we are down to the single elements, as I mentioned, the problems are sorted. So here we will see that the best case for the total time is n log n, which is n for each level and log n for the tree height. But it will have the worst case. What if we cannot get so lucky that, let's see, can you imagine about a bad example, like the worst example for one level? What will be, yes? What do you mean by array is sorted?
Let's say your pivot is from the left-hand side, your pivot is the first one. Each time you pivot, if it's already sorted, you will never split the array. The pivot will always be in place already.
Yes, great. So you are talking about the case that what if I'm choosing the smallest element every time in each level? Then what will be the height of the tree? Yes. So in this case, if you are choosing the smallest element as a pivot point for each level, what subarrays are you going to get? Actually, you still have 2 subarrays, but one with the size of 0 because there is no other element that is smaller than it. And on the other side, you have all the remaining elements. In this case, the height of the tree is not log n anymore. It is O of n. Does anyone see that? It might not be that intuitive, so So now you have the array of the n size. We know it has n. And we choose, let's say, if it's in the increasing order as an example. So this element will be the smallest of the total array. And it's actually, we will partition it into a pivot point of 1, and the right part, which is n minus 1. This is for the second level. And if we are not that bad luck, we might have some arrays here, but no, since it's the smallest element, it only has these two parts. And then we have the same, we get unlucky again. We will have another pivot point, which is the smallest one, and there's no other elements here. And then we will have the the array of n minus 1, or minus 2. And then you will have it go all the way to the bottom, so that it will be a pivot point and an element with only size of 1. So as you can see here, n minus 1, n minus 2, all the way to 1, so the height of the tree will be O of n. Okay? And if you have a problem viewing the graph, just let me know, I can redraw it. Okay? So this is the worst case for the quicksort. So suppose that instead of our pivot element splits array as, so now our pivot element splits array as unequally as possible. And instead of the n divided by 2 elements in the smaller half, we got only the 0. It means that the pivot point is either the biggest or the smallest element in the array. And now we have n minus 1 levels instead of log n. So for a worst case time, it is actually theta n squared. You can see that the worst case is very large. It's n squared. So does anyone have a problem on this part? Okay. But as we mentioned before, like for example for the hash map, we have the worst case scenario, but we also have the in practice expected time complexity. Let's call it the average case. So actually quicksort has better to be good in the average case. And the average case, it will be a little bit hard to explain, but first of all, do you agree that it's very difficult for us to get so unlucky that every time we choose the smallest or the best element? Does anyone disagree? You can raise your hand. Okay, so now you agree with me that it's very difficult to choose the worst case. So it's not common, it's real. And now let's think about the average case in the probability. Let's say that we pick the pivot point at random in an array of n keys. So, and we divide them into 4 quarters. We would say that for the middle half, it will be a good pivot. So why is that? Now we have an array. Again, we have an array. And this is our dream point. This is a pivot point that we hope we can get every time. But it is fine if we only get the keys here. So this is a 1/2, 1/2, 1/2, 1/2. And for the bound, it will be 1/2. 2/2 and 4.3 and 1. So we would say that if I get a key here, it's still okay. Why is it? Because let's say we have the worst case in the good keys. So we have a either a pivot here on the left or a pivot here on the right. What do we get? We get an array of a quarter of n, and at the same time, it is 3/4 of n. So instead of 0 elements, I still get 3/4 of it and 1/4 of it. It is not bad. Or you think it's bad? Okay, great. So I think you agree with me. So it will be a good pivot point. And now, so whenever the pivot element is from the position n divided by 4 to 3 times n divided by 4, the larger remaining subarray still contains at most 3/4 of the elements. And if we assume that the pivot point is always in this range, what is the maximum number of the partitions we need to get from n elements down to 1 element? Like this is the height of the tree. Thinking about the previously, when the size is equal, we will have log n. And now we will have the tree which has the 1/4 on the left side, 3/4 on the other side. So how many partitions does it need to reach from n elements down to 1 element? Now we have the recursion. So here we have the 3/4 of the element. So we will see that it will be 3/4. Let's say the height of the tree will be L times n. So after n L partitions of the n elements, and for each partition we will get 3/4 of it. And in that case, finally, it will reach 1 element. Does anyone have a problem with this equation? Okay, great. So now, I guess you all agree on this equation, and we just need to do the calculation. And as you can see here, n will be 4 divided by 3 to the l's. And then log of n will be L times log of 4 divided by 3. And therefore, L will be log of 4 divided by 3 times log n, which is smaller than 2 of log n. Do you have any problem on the equation? Yes? Yes? L equals log n divided by... Yes, you're correct. It's actually the log n divided by log of the 4/3. Yes, thank you. But still, it's within the constant. So we will need O of log n time of the good partitions to reach the 1 element. Okay? Great. So how often do we choose an arbitrary element as a pivot where it guarantees a decent partition? Since elements ranked between n over 4 and 3 times n over 4 will make a decent pivot. We get 1/2 of the time on average. And if we need 2, which is less than that, if we need 2 log n levels of decent partitions to finish the job, and half of the random partitions are decent, then on average, the recursion tree to quicksort the array, it will have approximately 4 times log n levels. So note that 4 times log n is still O of log n. Okay? Do you have any questions? Okay. So this O of n work is done by partitioning on each level. So the average time will be n log n. As n log n is there, n, which is n times the height of the tree, which is log n. Okay? If you have any part that you are confused or you need more explanation, it's okay to ask. Okay. So there will be a very mathematical way to do the analysis, and we will take an overview of it, but you can get into the details after class, because math is not that straightforward. So to a precise average case analysis of the quicksort, we can formulate a recurrence giving the exact expected time t of n. So we have the formula here. As you can see that we will have the pivot point index, which is p. So the total time is divided into, first is the left part, is t of p minus 1. If you remember, it's only the number of the left element, that is the number of the elements that is smaller than the pivot point. And then we also have the right part, that is the number of the elements that's greater than the pivot point. So it is n minus p. So now we have the total time, the summation of them, and it is divided by n. And it is divided by n, but we have the p, the pivot point. Recall that every partition we have done, the p will be the final index, the index of the final order. So we will have n pivot points, and they will be at the index 1, 2, 3, 4, 5, all the way to the end. So that's how we have the summation of the total work. Okay? Okay. And then we will also add the n minus 1 at the end to have the total. So this is the recurrence formula. And note that each possible pivot p is selected with equal probability. And the number of the comparisons need to do the partition is n minus 1. One formula we need to use here is called the harmonic numbers h of n. So it has a formula here. So if you have an array like from 1 plus 1 over 2 plus 1 over 3 all the way to 1 over n, and the summation will be approximately ln of n. So by using that, we will have the formula here. So from the equation here, we will have the summation of them, and then we get that. So we have the two parts, and so it's n2 over n, and we will have the total work of p minus 1 by, okay, like it's a symmetric the work, so they add them as twice of the summation, and then you will multiply the equation by n on both sides, so you'll have n of the t of n equals to the right part, and then you apply it to the n minus 1. So you will have the tn and also the t of n minus 1 total work. And in this case, you can calculate the tn by just subtract one from the other, and you will get the formula at the end, which is t of n divided by n plus 1 equals to t of n minus 1 divided by n plus 2 times n minus 1 over n times n plus 1. Do you have any questions on the calculation? Yes?
Can you explain again why you see the 1 over n?
1 over n? Because you have the p you have n pivot points in total. And every pivot point is selected with the equal probability. Yes. And yes?
Do we have to know this for the test, or?
From my experience, you need to know the basic ideas, and even though professor give you the test on it, it won't be so difficult. It will be some easy calculation. But like you need to know how to calculate the current total work, like T of n. How do you get that? You have the time for the partition, and you have the time for the merge, and you add them together. That's how you get the n, T of n. And when you apply n minus 1, it means that you replace the n by the n minus 1 and calculate the other work. And then you will do some subtraction or multiplication to find the answer you want. Okay. In here, substituting an of the capital A of n divided by n plus 1, it gives the formula here. And now we can see that from the formula here, actually it will be 1.38 n log n. And 1.38 is a constant. So that's how you get the time complexity. Any questions?